Rightio. Question 1. Here, don't be confused by this, that we've got a flange here. So we've got two 50 kilonewtons pushing down. Your diagram you want to draw, therefore, is going to be something along the lines of, if I can draw straight, which I can't. $40 going that way, $100 going this way, 250s. We'll have a reaction here, which we don't really need, RA. Just as a to get you in the mode of template solving, and you know, you're looking at this problem, wondering what to do, you can always start off by resolving your forces here. We've got the RA, but as I said, we don't really need it. So we'll sum our forces. We're going to do this in the x direction, going left to right. So I've got RA take away 100 plus 40 equals 0. RA is going to be 60. Didn't need it, but that's good enough. Now you don't really want to draw loads of free body diagrams, just want to use the one free body diagram, especially as this is multi-choice, and say to yourself, what am I going to be doing with this? Well, I'm going to be identifying my sections. So I've got a section 1 here, and I've got a section 2 here. I tend to work from right to left, and in my section 1 I will do a cut where I will expose the internal force, and I'll do a cut in my section 2 where I expose the internal force. So I can imagine that this internal forces are always going to be balancing where I do the cut. So we've got an internal force F1. Along this particular cut, we've got F1 going this direction, and again, for convention, it's a bit like your method of sections. You point your arrow going away from your initial point here. So it's going to always kind of be, if you're going from right to left, it's always going to be pointing right to left on the right hand side of the section. So again, in our second section, we'll do a cut and we'll expose the force F2 there. But currently, if we look at the body from the outside, as it were, we can't see those internal forces. So what you're going to do now is go through the beam and imagine that we're going to do a cut, take this cut here, and we ignore everything then on the left. So all of this we imagine we can't see. Okay. So if we can't see that bit on the left of this line, I'll go back for left of this line here, the only forces that I can see when I start resolving them will therefore be my minus F1, because it's pointing left to right, and then I'm going to see my force going plus 40 in this direction here. So that equals 0. So F1 will equal 40. So that will be the first thing. Okay. And then when we come to this section 2 and do the same thing, we're going to be imagining that all this bit to the left here is being ignored. Now, when you look back to the right of this line here, the F1s both cancel out, so you ignore them. In fact, they're not being exposed. There's no cut there, so you can't actually see them. The only exposed force, the only exposed internal force is going to be this F2. So imagine now you're taking your cut at this F2 location, and that will be, therefore we can see the minus F2. And now we're going to look right of our line, and we can see that we've got 100 going right to left, and we've got 40 going off in this direction here, left to right, and that equals 0. So let's rearrange that. F2, I make that to be minus 60. I'm being a bit liberal with my units and whatnot. I'm working in kilonewtons. The next thing for the question is asking us where does C move. So therefore we want to look at the compressions and extensions in both sections, sum them up, and then we're going to get the total movement. So the equation we're going to use there is that the displacement is based upon the sum of the internal forces, the lengths of those sections, divided by the Young's modulus of those sections and the cross-sectional area of those sections. So we've obviously got section 1, and it's got length 1, E1 and A1, and then we've got F2, L2, E2 and A2. Now for this bar we can see it's actually stays as a constant diameter. Whoops. And we've also got the fact that it's still all the way through. So my E1s and my A1s are all going to be the same. So my first external force will be the F1 force. So that'll be my 40. You want to keep your signs, and that will tell you which way you're going. So if I end up with a negative, that will tell me, because I've been consistent with my signs and my directions. If I end up with a negative, I'm going off in this direction. If I end up with a positive, I'm going off in this direction. So 40,000. What's the length of section 1? Well, that's going to be 0.4. E is 200 times 10 to the 9. And then I need to put in make the area, so I'm going to use pi 0.02, square it, divide it all by 4. And similar for my other section. Here, however, my F2 is going to be a negative, so minus 60,000. It's a longer section, so it's 0.6 in meters. We've got the same Young's modulus, 200 to the 9, and you've got pi 0.02 squared, all divided by 4. Put your numbers in your calculator. Well, I've already done it, so I won't this time, but you'll end up with minus 0.318 times 10 to the minus 3. Use your eng button to get your minus 3s. And that's in meters, so obviously in millimeters we are going to ignore 10 to the minus 3, and we can get the answer B. Okay.